Okay, so that was basically the solution for task number 1, just to access all your data files from the data folder. The idea to go through it is that, again, I'm not sure how much of coding experts you are, but yeah. The idea is to have everybody moving so we can continue with other more interesting exercises. Please let me know if after you run these, it works for you. Okay, some people is having some issues. Some people is having issues with the install of PyXDF. That's the library that we will use to read the files. And the easiest way how I do it is once I open the notebook, I go to the terminal and just pip install. I think it's called like that. And I just run it. It should work. And then it should let you run this first one here. If somebody is using Visual Studio, it's very similar, but the terminal, you will find it somewhere around here. Okay, so let's maybe continue with the, okay, maybe we can a little bit with the other exercises. And in case it is not working for you, maybe you can just follow along. It is also very interesting, more about the programming part, also just to get to know how it is done, so to say. So if for somebody it's not working, maybe for your neighbor it is working, and you can work together. Okay, so that was task 1. Then task 2, well, after this, we will have basically all our XDF files, as I said before. XDF is a very specific format. It's not like CSVs. CSVs are very easy and very common, but they're also very heavy, so to say. And that's why XDF tries to structure the data differently to save space, etc., etc. So afterwards, we will have all our, as I mentioned, all our XDF for test 1, 2, and 3. They have different lengths, as I mentioned before, because we want to test our latencies are constant through time, and that's why. So as I mentioned during the design for our latency test, we have Unity and we have EEG. For Unity, what we did during our game is anytime the color changed from gray to white to black so that the light sensor could detect it. And that's why we use those colors. We sent on a stream called visual, right, from Unity, some numbers or some sort of data anytime that happened. And then for the EEG, we have 2 streams. One is called open by markers, which is the one that is usually used in classical paradigms or classical setups, where you will basically send anytime an image sent, you will send a marker with a timestamp, etc., of when that happened, so that you can analyze later on. And then we have open by signal here, which is all our, in this case, 64 channels, because we use that sort of cap, but we are only using 1 channel, which is, if you remember from somewhere, from here, we had a light sensor connected to the amplifier. This is the 60 or 128 channels. We are only using 1. And through that one is that we are sending all the voltages of the light sensor detecting changes in the environment. So XDF usually will give you two important components, which are time series. Oh, sorry, yes. So yes, I'm going there. So we have LSL was what I mentioned here previously. LSL is lab stream layer, which basically you install it in your computer to detect all the streams that are in that network, right? So you are sending from Unity, right, some streams or some data in the system, and you're also sending to that very same system the changes in voltage from your amplifier. And what lab stream layer does, which is lab recorder is simply a name, is simply a name for the app that you install in your computer, right? But LSL is basically the one that takes both streams, synchronize them, and put them in the same time stamps, so to say, right? So that all the streams that are arriving, you can, with a lab stream layer, collect all sort of data. So button presses from Unity, you can collect EEG, you can even collect voice recordings, like all of that. If you connect them to the same network or to the same computer, they are detected, as I mentioned here. So all of these ones in green are the streams that are arriving, as I was mentioning. So we have open vibe signal, which is our amplifier signal. We have visual, we have eye tracking data, etc., etc. So all of those are detected by lab recorder or lab stream layer and put sort of like in the same time. So XDF files will give you two important components, which are time series. In time series, you will have all your data. So for the time series component of EEG, you will have all your changes in light or intensity, or how you want to call it. And the second component, and for Unity, let's say every time the color white was appearing, you send into a system a 0. So all of that moment, or all of those zeros are the ones that are being collected in this time series component. And then we have a second component, which are the timestamps, right? So we have, do we have maybe? So anytime sample arrives into a system, it comes, let's say you send zeros, and then it comes a timestamp, time 0. Then the next sample, time 1, time 2, time 3, and those are your components that are saved in the XDF file. So task 2 was basically, or consists in using XDF file to import your data sets. Yep. And for that, we have some help in here. So if you click in there, you will go to the definition or how to use XDF files, or how usually it is imported, which basically tells you something like, take your XDF file, and it will give you some information, some data, which is the data you wanted to store, meaning those components, your timestamps and your time series, and some header. We don't care about the header, we just want the data, right? So task 2 is to import the files. Yes?
I think the data is the way the problem is.
Okay.
In the example, I think it's 9.2. We index 2 and streams only have. And yeah, you get a you get from the lowest so you need to.
Okay, so let's do the following so that we can follow a little bit and we don't get stuck just in loading the data. I will just show how it is and I will explain what is around it. So when we load the data, it should look something like this, right? So before we have mentioned that we wanted our recordings, right? Because if you remember from the website here, it is telling you that you have to sort of like, here, give the name of the file in that folder, etc., etc. But previously we had sort of like put all our recording names in this variable or in this dictionary called recordings. So if you come here, we have recording 0 is this file, recording 1 is this file, and recording 2 should be this file, right? So if we want to access one specific recording, this is one way of doing it, right? So we point to a data folder, we point to recording 0 in this case, right? And file is just pointing to this file here, right? When we load it, what we have is, we save our data in a variable called streams. Once we display it, what we have is this huge dictionary, right? Right now I cannot scroll because this is a presentation, but if I were to do that, it is just very long. It is basically a list of dictionaries. And it contains some information. For example, here we have that the name of the first stream is open by markers. We don't care about those because we didn't use them. It shows you what kind of format of the data it's in there. For example, what computer hosts the data, because if you remember from the presentation here, we use 2 different computers, right? One for EEG and one for the VR. And the only reason why we used 2 computers was actually to decrease the complexity, because you have a very, very heavy Unity game at the end, right? That is running on a specific computer, needs all the sources to comply with the keeping the sampling rate. And if apart from that, meaning apart from running your game, you also collect the data from that computer, then the computer just gets too much tasks, so to say, right? That's why we use 2 different computers, one to run the program, the Unity environment, and the other one to collect the data. So yeah, after we load the data, this is what we have. And then we can start looking at what exactly our streams contain, right? One way of doing it is, for example, accessing stream number 2, because as I said, they are ordered. So for example, stream 0 is open by, etc., etc. So if we access stream 2, info and name, we will have the name of that specific stream. We can also access components, as I was mentioning earlier. So if we type streams 2 and timestamps, it will give us all our timestamps that were saved during recording. And if you access, for example, streams 2, time series, then you get all of the information that you really care about. In this case, for example, we're accessing channel 64, which is where we plug our light sensor detector, right? And in time series, we will just have these changes in intensity, right? I may just continue. I don't know how much time do I have?
20 moments.
Exactly. So we will likely not go over all of the exercises as I planned, but I can show you more or less how they should look like, and maybe later on you can have a look at them and ask questions and stuff like that, because it's also really interesting to play with that data. Okay, so for example, as I was saying, if we access stream 2 timestamps, we have just a long array of timestamps. One interesting thing that we can notice here in the timestamps is that those timestamps are not normalized to 0. That means just lab string layer, which is the one that is detecting both devices, is giving a timestamp for both, but it sort of looks like random. So this is timestamp 0. So this is for the very first sample that arrived into the system, and that lab recorder decided to call it 237,978, whatever, right? So later on, we will have to process these timestamps as well. If we look at, for example, the stream names for all of the stream saved in our XDF file, we have that open-byte markers is in the position 0, so to say. Visual, which is from Unity, is in position 1, and open-byte signal, which is our EEG signal, comes from in position 2. Then our goal was to go through some basic definitions or the functions that we need to create in order for us to take this huge XDF file and format it in a way that is understandable, because if you just show this one. So if you look at our dictionary, this is how the XDF file looks like inside. It's just a mess. It's really, really not visually appealing or anything. Okay, so to create those functions, first we wanted to, for example, create a function that only access those streams that we care about. We don't care about the other ones. Sometimes you can send only 2-3 streams. Sometimes you send many, right? When you are tracking, for example, I positions and directions, you have to say X, Y, and Z positions for I, X, Y, and Z positions for head, etc., etc. So they end up being a lot. So this is one of the first things you want to do. Then afterwards, we might want to say, for example, the host name for EEG and Unity. So just to be sort of like in the safe side that they are indeed all the time being recorded from the same computers, etc., etc. Yes? Yes, we can do that. Actually, I can share the PDFs with you so you don't copy paste. Oops. So, well, we can save the host, but this is simply like metadata. We can access the timestamps for our streams. So in this case, for example, we want the Unity channel and we want the EEG channel, and we want those timestamps for each of them, and we want to retrieve them, right? Then we can create another function that basically, as I mentioned before, those timestamps are not aligned, so they don't start at 0. We want them to start at 0, right? This is one way of doing it with an array. So for each time or each sample in the system, subtract that sample from the previous one for all the length of the array. And then what that will give you is, instead of 2, 7, 8, 9, whatever, it will give you 0, 0 point something, 0 point something, and so on and so on. Then we have some, the interesting part, which is basically calculate the latency. And for the latency, we just want to know from timestamp 0 to timestamp 1, how much time is it in there, right? What's the difference? Yes? Yeah, so exactly. So the idea is that we want to measure, right, that the latencies in Unity are all the time the same. That means that the system is sending the samples into a computer all the time at a specific time, which is or exact or more or less. And that's what we want to find out, if it is happening or not. One way of doing it in here, this one was for, for the latencies, right? Whereas we just say, okay, just subtract each timestamp difference from of the current one and the next one, so to say, for the entire arrays. Then we want to find out or retrieve. So as we retrieve the timestamps, we also want to retrieve the data, what was actually saved from Unity and from the EEG. And it's just the exact same thing. So instead of accessing timestamps, we just access time series. And as I mentioned before, for example, here we are accessing the channel 64 because it was where we plugged our light sensor. Finally, we want to calculate the durations, for example, because we want to measure or want to know how long each of the tests was, and just to later on have sort of like a comparison between tests, right? So how you can do it is subtracting timestamp one, the last timestamp from the first one and dividing it by 0. That will give you, dividing it by 60, that will give you a time in minutes, right? Then we want to calculate the average sampling rate. We mentioned before that we made sure that Unity was at 90 Hertz and EEG is all the time at 1024. So we just want to make sure, hey, that was the case based on our timestamps, right? One way of doing it is by applying this little formula. And finally, we can create an entire protocol, right, that will go through each of our, well, I mean, with the functions we defined before, right? So we can load the data, we can select specific streams, you know, with our previously created functions, and that will give us the entire data set across all the recordings, right? Finally, we can have here, for example, an interesting look at a sort of like an overview. In here we have, after we did all the pre-processing, we find out that, for example, for text one had a duration of 3.9 minutes, the second one 7, and the last one 12 minutes. We see that the EEG, well, here what I wanted to do was to check that both devices had the same duration, right? So if I check the Unity timestamps and the EEG timestamps, and they have different durations, well, something was wrong because they should have the exactly same one. The Unity sampling rate was very constant at 90 Hertz, and the EEG as well. And here we have our two different computers. And then here is when we basically retrieve all our data already stored in something more comprehensible, more readable, etc., etc. And I mean, for the EEG and for Unity, because you were sampling EEG at 1024 and Unity at 90, so if you try to put this into data frames, they will have different lengths because Unity is sending less samples than EEG, right? You're sampling 1024 samples every second for EEG and only 90 for Unity. So you will have to store them in different CSVs. So then we can do some descriptive statistics, which is what we wanted to do, check the latencies. So if we look at the latencies here, we have, for example, that the mean, right, sampling rate, or the latency between one sample and the next one for Unity, yeah, in this case for Unity is 0.011, right? And that's what it's telling us is basically that from one sample to the next one, Unity always is sending it with a difference of 0.11 milliseconds, right? So from one sample to the next one, it takes to travel from our headset to the computer 0.11 milliseconds, right? And then if we check for EEG, we have this, is almost 0, right? So it's very, very, very fast. EEG sends its samples into the system very fast. Yes?
The computer state is kind of subtracted the constant of that, right? So it's the inverse of the sampling frequency, not like this.
Sorry?
Like the computer latency is subtracted like 1 times 10 from another time.
Mm-hmm.
But it's the it's 1 to 1%.
Yeah, so as I said before, latency, you can understand, like people use the word latency just simply to describe the difference or the time it takes for samples to travel from A to B, and simply the distance between those samples in time. The point is you're saying that is not what you would call latency, or if I didn't get your question correctly.
You don't get wide from 1 times the C, you get like we have consequent measurements of time, right?
Mm-hmm. Yeah.
We will get the difference in time.
No, so the point is when you are designing with Unity, one of the biggest challenges is that the system is always sending the samples in a constant time. So if you don't make sure that Unity is sending samples at 90 hertz, so let's say Unity sends at 90, 80. So if instead of here, for example, well, in the previous one, getting the sampling rate at sometimes 80, sometimes 70, sometimes 80, that will create differences in how much time at each sample takes to arrive into the system. And therefore, it's important to make sure that the differences in time between samples is always a constant. That is just telling you that the system is indeed working as you wanted it to work. That's why you want to measure the time between time 0 to the next one, and the next one to number 2, from number 2 to number 3. You always just want to measure that distance. It's not all of the times with respect to 0, but the times between each of the samples. Because sometimes it could be, sorry? Okay, let's maybe continue because we are running out of time. But if you have any questions, I'm happy to discuss later. Okay, so here we say that Unity is sending its samples very constant and almost at time 0. As I said, it takes 0.98 milliseconds for each sample of EEG and 11 milliseconds for each sample for Unity. And then we can visualize this if we want. And we would have something like this, where we have on the top all our EEG samples and the distribution. So if EEG was sometimes sending with different latencies and so on, what you would expect would be like some outliers or something like that. And what it's telling us, for example, for the EEG is that it's very constant around this number. And for Unity is, interestingly enough, telling us, yeah, there is some differences, right? So the average is 11 milliseconds, but sometimes, as you can see, there are some outliers. Some samples arrive either earlier or faster or slower into the system. And if we visualize the data that we collected from Unity and the data that we collected from the light sensor, what you're expecting, right, is that both of them through time behave very similarly, right? And if our timestamp alignment was correct. So If we, for example, visualize the first 5 seconds of our recording, a random recording of them, what we have is this. So on the top, we have the unity markers. So every time the color change from white to black to gray, I don't remember the order. This is what we have in the light sensor, right? So what we can see is that while the sensor is not detecting any light, it's corresponding pretty nicely with the markers that Unity is sending of, hey, let's say this is white, so I'm displaying white at this moment. The light sensor is saying, yes, I'm seeing that, and so on for the rest of the recording. So yeah, as conclusions, we have that the sampling rate for Unity and EEG are very constant through time. The latencies for both devices, let's say, is irrelevant of recording duration. So the recording could be 3 minutes or 12 minutes, and it will stay the same. And therefore, we can use lab stream layer very nicely to synchronize different devices and collect brain data. Yeah, that's basically it.
Thank you so much. Thank you much. As you mentioned before, you will probably be staying in the comments, so we can catch you near the copy. If you have any more questions, and we're going to take 15 minutes break before the next song.